Hello and welcome back to another episode of Math with Stone. Today we're going to be continuing gravity, but we're going to use the formulas a little bit differently because it'll just be easier that way. When you're given a scenario where you're told the radius of something is like 2.5 times bigger or the mass is 4.6 times bigger like we have here, you could go through the formulas and you could figure out what 2.82 times the radius of Earth is and 4.6 times the mass of Earth is, but that would take a lot longer than just dealing with it proportionally, okay? So here, if we wanted to figure out essentially the gravity on Krypton, which is what matters, it doesn't really matter that Superman is dropping this rock 3 meters above the surface of Krypton. That distance is kind of insignificant, so to speak, compared to the actual radius of Krypton. So it would be so minor that it's not going to affect the gravity. Yes, gravity will be a little bit less, 3 meters above, than actually on the surface of Krypton, but not enough to make that much of a difference. So we're not going to focus too much on that. We are going to focus on the radius and the mass of it. All right, so essentially what you can do is you can say the gravity on Krypton compared to the gravity on Earth, which I probably should have used a small lowercase g there because big G stands for something else. Gravity on Krypton, gravity on Earth. Well, that would be the gravity formula, which would be G times the mass of Krypton divided by the radius of Krypton squared. And that would relate to G, gravitational constant, mass of Earth divided by the radius of Earth squared. Well, what's going to happen here? Well, the gravity is going to cancel. And we also were told some information about the radius of Krypton is 2.82 times the radius of Earth. So you can use some substitution to just substitute in. Instead of writing the radius of Krypton here, you could write 2.82 times the radius of Earth. And instead of writing the mass of Krypton, you could write 4.6 times the mass of Earth. So let's do that. So we got 4.6 mass of Earth. And then here we would have 2.82 radius of Earth squared divided by the mass of Earth divided by the radius of Earth squared. Okay, you can do keep, change, flip, and multiply here. So this is going to end up going onto the top of the fraction, and when we do that, we would have the radius of Earth squared moving to the top and the mass of Earth just being on the bottom. Well, what do you notice about some of this stuff? We have 4.6 times the mass of Earth. Technically, you can multiply those together, but if you think of the mass of Earth like a variable, it will definitely just cancel out. And here, if you wanted to kind of like distribute that exponent, you'd have 2.82 squared and the radius of Earth squared. Well, the radius of Earth squared would just cancel out. And that would leave you with 4.6 out of 2.82 squared. And if you do that math, you get 4.6 divided by 2.82, and you end up with 0.59 approximately. Now, 0.59 tells you the ratio of the gravity of Krypton. I did it uppercase G again. Gravity of Krypton divided by gravity of Earth would equal essentially 0.59. So if you solve for the gravity of Krypton, you could multiply by the G of E, and you would get the gravity of Krypton is equal to 0.59 the gravity of Earth. And if you know the gravity of Earth is either 9.8 meters per second, or you could think of it as 10 meters per second, the gravity of Krypton, therefore, would be 0.59 times the gravity of Earth, which is 10 meters per second squared. And if we do that, you would find out that gravity on Krypton is approximately going to be 5.9 meters per second squared, which would be the acceleration due to gravity, which was not the main question. The main question was, Superman dropped a rock 3 meters above the surface of Krypton. How long does it take it to reach the ground? Well, we now know the gravity on Krypton is 5.9 meters per second squared. So if the gravity on Krypton is 5.9 meters per second squared, you can use the formula, the kinematic formula, delta x is equal to VO times time plus 1/2 AT squared. And the difference here is that gravity is not going to be 10 meters per second. It's going to be 5.9. And there is no initial velocity because he dropped it. So it will take approximately, let's find out, 5.9 times a t squared. And he dropped it a height of 3 feet, so it went down by 3 feet. 1/2 times negative 5.9 times t squared. If you do those calculations, we would have to divide negative 3 divided by 1/2 divided by negative 5.9, and then you would square root that answer, and you would figure out the time is about 1 second. That is as close to 1 second as you could get. It's 1.008 seconds, and I was out of room, so that's why I didn't do the math on paper. Time will equal 1.008 seconds. It's not a lot of time. All right. Planet X is half the radius of Earth and half the density of Earth. What is the acceleration due to gravity on planet X? This is going to involve a little bit of an AP Physics 2 idea, because density is more of an AP Physics 2 material, but it's still kind of neat for gravity. So gravity would equal gm divided by r squared. And one thing about gravity and the mass, we have it in terms of density. Well, density, in case you were wondering, density is equal to the mass divided by the volume. So if density is equal to the mass divided by the volume, the mass would equal the density times volume. So we're going to have to replace that. That's the AP Physics 2 part. Another aspect of AP Physics 2 is we call density this Greek letter rho, which is like a weird-looking P. So you'd have gravity times density, which would be the Greek letter rho, times the volume. Well, most planets are considered a sphere, so the volume of a sphere would be 4/3 pi r cubed divided by r squared. And the r squared and r cubed would cancel, and you would have gravity times rho times 4/3 pi r. And that would equal the gravity on essentially like the G formula in terms of density. Okay, we didn't actually deal with the 1/2 part and the 1/2 part. We haven't set up the proportion. We just figured out the gravity formula in terms of density rather than in terms of mass. Okay, so next thing we can do is figure out the gravity of planet X compared to the gravity of Earth. So we set up that proportion, and that would mean that we would have these two formulas here, and we would just have to put in 1/2 for the radius and 1/2 for the density. So we would have big G times 1/2 the density, so 1/2 p rho, times 4/3 pi 1/2 r, and then it would just be equal to the same thing but for Earth, which would be without the 1/2, G times rho times 4/3 pi r. And then a whole bunch of stuff's going to cancel out. The big G is going to cancel the gravitational constant. The rho is going to cancel. The pi would cancel. The r would cancel. And you end up with 1/2 times 1/2, which is 1/4, times 4/3 divided by 4/3. Well, the 4/3 would even cancel. I didn't even see that. So we would have 1/4. The G of X divided by the gravity of Earth would equal 1/4. Which means the gravity on planet X would equal 1/4 the gravity on planet Earth. All right. And it's asking for what is the acceleration due to gravity? What is the acceleration due to gravity? Well, G of X would equal 1/4 of 10 meters per second squared, which means the gravity on planet X would be at 2.5 meters per second squared. All right. We got two more problems for you real quick. This next one is going to be talking about gravity fields in relationship to the moon. So I'm going to focus on the moon part. And is there a point between Earth and the moon where you would be weightless? And is there a halfway point? You know what? I'm debating whether or not to wait on making this a separate video. I think it's a good stopping point because the next two questions kind of deal a whole lot with space station-y stuff. So until next time, everybody, I will see you later. If you want to know when and if there is a halfway point as well as artificial gravity, stay tuned for the next video.